In the previous lecture, we have started to deal with the theory of Drude-Lorentz regarding the free electron theory of metals. And you have seen in Drude model, we assume that the free electrons, that is the valence electrons of a metal, just behave like the molecules or atoms of a perfect gas or ideal gas. Okay. So according to this theory, the kinetic theory for the ideal gas can be applied for discussing any behavior of a metal. Okay. We have also seen in that lecture what are the important applications of this Drude model. I have told you that this Drude model successfully explains the various properties of metals. And among those properties which can be successfully explained on the basis of Drude model, I have listed in my previous lecture. And you have seen two important applications of this model in that lecture, and those were actually the explanation of Ohm's law and the thermal conductivity of the metals. Now in the present lecture, we are going to see the another important property of metal that can be explained on the basis of this Drude model. And this is regarding the relation between the electrical and thermal conductivities of metals. Actually, the relation between electrical and thermal conductivities of metals was established by two famous scientists named Wiedmann and Franz. So this relation is also known as, or you can say popularly known as, Wiedemann-Franz law. Okay. So, but this is just an application of Drude model. So we are just dealing with the problem of application of Drude model, and in this regard we will see how this Drude model is successful in explaining the Wiedemann-Franz law. In other words, you can also say applying this Drude model we can derive the Wiedemann-Franz law. As you know, this Wiedemann-Franz law establishes a relation between the electrical conductivity and the thermal conductivity of metals. Actually, it is an experimental fact that all good conductors of electricity are also good conductors of heat. It means a material which conducts electricity also conducts heat energy. Okay. So on this basis, Wiedemann and Franz gave an empirical law relating the electrical and thermal conductivities of metals. Okay. In fact, it is also found that the electrical conductivity and the thermal conductivity of metals depend on temperature. In fact, it is found that with rise in temperature, the electrical and thermal conductivity decreases. In other words, you can also say if temperature is decreased, then the electrical and thermal conductivities both will increase. Okay. So definitely there should be a condition of temperature while we will relate these two conductivities. So taking this fact under account, Wiedemann and Franz law states that the ratio of the thermal conductivity and the electrical conductivity at a particular temperature is same for all metals. It means you have to fix a particular temperature, let us say at room temperature. And if at room temperature you will find the thermal conductivity and the electrical conductivity of different metals, and you will find the ratio of the thermal and electrical conductivities of different metals, but at same temperature, let us say at room temperature. then it is found that ratio is same. Okay. In other words, you can also say that at a given temperature, at a particular temperature, or you can also say at a constant temperature, the thermal conductivity K of a metal is directly proportional to the electrical conductivity sigma of that metal. Okay. So mathematically, you can formulate this law, that is Wiedmann-Franz law, in this way, that the thermal conductivity K of a metal is directly proportional to its electrical conductivity at a given temperature. And so when you will remove this sign of proportionality, you can write K is equal to some constant times sigma, or you can write that K over sigma is equal to constant. This is the mathematical form of the basic law provided by this is the basic form of the Wiedmann-Franz law, you can say. But this ratio K over sigma is temperature dependent. At different temperature, the value of K by sigma is found to be different for the same metal. This is different at different temperature. So taking this very fact under account, Lorentz has extended this law, taking this fact of temperature dependence of this ratio. According to Lorentz modification, this ratio, that is ratio of K and sigma, is proportional to the absolute temperature T. It means if temperature is increased, the ratio K over sigma also increases in the same ratio. And if temperature will be decreased, this ratio of K and sigma will decrease in the same ratio. Okay. So when we apply the Lorentz modification, then we can state this Wiedmann-Franz law in this way, that K over sigma is directly proportional to the absolute temperature T. And so that you can write K over sigma is equal to a constant times T. And therefore, you can write equivalently in this way, K over sigma into T is equal to a constant. And this constant is in fact a universal constant. It will be same for all metals. When we will derive this law or prove this law, you will see that actually this constant is a universal constant. Okay. Now here you can see that basically this Wiedmann-Franz law is stated in this way, that K over sigma is equal to constant at a given temperature. And after after Lorentz modification, we state this law in this way, K over sigma into T is equal to a universal constant. So nowadays, this form K over sigma T equal to constant is assumed as this law. So whenever a question will be asked in the form of objective question, let us say a question is like this, what is Wiedmann-Franz law? And in option there is K over sigma into T equal to constant, and also in another option you are given K over sigma equal to constant. What will be the correct answer? Correct answer will be this. You have to write the correct answer in this form, K over sigma T equal to constant. So now we assume the mathematical form of this Wiedmann-Franz law in this way, K over sigma T equal to constant. Okay. So this is the Wiedmann-Franz law, okay, which relates, you can see, the thermal conductivity K and the electrical conductivity sigma of metals at a particular temperature T. Okay. Now we will see how this law can be explained, on the basis of Drude model. Or according to Drude model, every metal has free electrons, a large number of free electrons. And when you say free electrons, we have already learned these are actually the valence electrons which move inside the metal surface under a constant potential with a large speed randomly. Okay, and so according to Drude theory, these free electrons are just equivalent, just like the molecules or atoms of a perfect gas. Okay. In fact, Drude model states that these free electrons are responsible for both the thermal and electrical conduction. It means a metal conducts electricity. Why? Because it has free electrons. A metal conducts heat energy. Why? The answer is it has free electrons. So free electrons are the vectors which are responsible for both electrical conduction and thermal conduction of a metal. If free electrons are not present in any material, then those materials cannot conduct electricity and heat. Okay? So the cause of the electrical and thermal conduction are actually the free electron. So that the thermal conductivity and the electrical conductivity can be explained on the basis of this Drude theory of free electron of metals. Okay? In fact, how we can explain it, we will learn in this lecture. Although we have already discussed how this Drude model explains the electrical conductivity of metals. So here we will write down the final expression for electrical conductivity which we have obtained in our previous lecture. And after that we will calculate the thermal conductivity of the metal on the basis of this Drude model, and then we will explain the Wiedemann-Franz law. Actually, you have seen that when there is a specimen of metal like this, in absence of any external electric field or potential gradient, the free electrons inside this metal moves randomly. And so the probability of crossing any section of this specimen from left to right and from right to left of electrons are same. In other words, you can say the equal number of free electrons passes through this section from left to right and from right to left. So the net flow of charge through this section is 0, and so no electric current is produced. But when you actually connect the two ends of this specimen by a voltage source, in other words, you can say when we set up a potential difference or potential gradient across this specimen, then an electric field is produced inside the metal. In electrostatic condition, when you do not apply any voltage across the specimen, that state is called electrostatic state. In that condition, there is no electric field inside a conductor. But when we apply this voltage, then electric field is produced. And due to that electric field, our free electron experiences electric force. And under that electric force, the free electrons drifted in a particular direction in just opposite to the applied electric field. So this average drift of free electrons in a particular direction under the electric field or potential gradient give rise to electric conduction, or you can say it constitute electric current. Okay, so in this way the electric conduction takes place. Okay. Similarly, if there is a conductor, let us say this, and you set up a temperature gradient, let us say this end A of the conductor is at temperature T1 and B is at temperature T2 and T1 is greater than T2. Then there will be a temperature difference or temperature gradient between the two ends of this specimen, and due to this temperature difference, energy flows, or you can say thermal energy is carried by the electron in this particular direction, and this flow of thermal energy through a section in a particular direction gives rise to thermal conduction. So I have mentioned it here that transfer of energy of random motion in a particular direction due to the temperature gradient causes thermal conduction. Okay, so you can see for thermal conduction and for electrical conduction, free electrons are responsible, and thermal conduction will take place when we set up a temperature gradient, and electrical conduction will take place when a potential gradient or potential difference is set up across the given specimen of the metal. Okay, so taking this idea under account, we can easily obtain the expression for the thermal conductivity and the electrical conductivity of a metal, taking the results of the kinetic theory of gases for a perfect gas under account. I am repeating the things that any equation of kinetic theory of gases can be used for the electron gas too according to Drude model. Okay, so whenever needed, we will use the result of the kinetic theory of gases for this electron gas. Okay, so now let us see first of all the calculation of electrical conductivity of the metal on the basis of this Drude model. Actually, as I have told you, this problem has been already dealt in our previous lecture. So I am writing here our final result which we have obtained for the electrical conductivity of metal in our previous lecture. You have seen that the electrical conductivity, which is denoted by the symbol this sigma, is equal to Ne square tau over m. This result was derived in the previous lecture as you have seen. Okay. Now in this result, you know what is this N? N is actually the free electron concentration. When you say free electron concentration, what does it mean? It means this is number of free electrons per unit volume of the specimen. In unit volume, how many free electrons are present, that is denoted by the symbol N. And you know, E is the charge of an electron, which is called electronic charge, and M is mass of an electron. And what is this tau? Remember, I have discussed this tau in our previous lecture. This tau is called actually relaxation time. And what is this relaxation time? You know, during its random motion, the electrons collide with the lattice, that is the positively charged ions, and randomly changes its direction. The distance between two successive collisions is called free path, and the time taken between two successive collisions in general will be not same. So when you will obtain the average value of the time taken between two successive collisions. Let us say first collision takes place here, second collision here, and the time taken between these two successive collisions is T1. And then here our electrons suffer collision, and this time is T2. So when you will take the average of the time taken between two successive collisions, then you get the value of this tau. This tau is so the average value of time per collision. Okay, and this is called actually the relaxation time. And you have also seen that this tau is equal to lambda over Vrms. All these things we have learnt in our previous lecture. Here lambda is called mean free path, and mean free path is the average value of the free paths Okay, if you say that the distance between first two collision is lambda 1, second and third collision is lambda 2, third and fourth collision is lambda 3. So when you will obtain the average of these lambda 1, lambda 2, lambda 3, then you get lambda, and this is called mean free path. And in kinetic theory of gases, you have learned about this mean free path. Okay. If you have not learned, you can watch my video on mean free path in the playlist of my channel named Thermodynamics, where you will get a detailed discussion of mean free path. Okay. So tau is defined as lambda divided by Vrms. So when you will replace this tau by lambda by Vrms in this expression for sigma, what will be the expression for sigma now? So sigma is equal to Ne square lambda divided by m times Vrms. Okay, Vrms. But as I have told you, according to Drude theory, the free electron behaves like molecule of a perfect gas. Okay, and we simply say that free electrons, we simply say that these are electron gas. Here gas, electron gas is made up of not molecules but electrons. And I have also told that any formula of kinetic theory for perfect gas can be utilized for the electron gas. And you know from kinetic theory of gases that the average translational kinetic energy of a molecule of a perfect gas is equal to 3 over 2 kb into T, where kb is a universal constant. You know, this is called Boltzmann constant. So for electron, you can equivalently write that half m Vrms square. This is actually the average translational kinetic energy of electron. That will be equal to 3 by 2 kb into T. This result has been written on the basis of kinetic theory of gases. Okay, and you can use this for this electron gas according to Drude model. Okay, so from here we can easily find the factor m into Vrms from this result. You can see this 2 and this 2 will cancel out, and m Vrms will be equal to what? You can see this m times Vrms will be equal to 3 kBT over Vrms. Okay, so now finally we will replace this m into Vrms present in the denominator of this equation 1 by this value. So using this result in equation 1, we get sigma equal to Ne square lambda divided by m Vrms. But m Vrms, you can see this is 3 kBT by Vrms. So this will be 3 kBT times Vrms. Okay, and actually this is our final result for the electrical conductivity of metals. Okay, now we will obtain the expression for the thermal conductivity of metal by using the Drude theory. And for this we consider there is a specimen of metal, as you can see in this figure, and its two ends are maintained at two different temperatures, and A is maintained at temperature T1 and B is maintained at temperature T2. Here there will be a temperature difference. If we assume that T1 is greater than T2, then you know in this condition there will be a flow of energy or thermal energy from end A to B, and this actually constitute the heat current. Heat energy flowing per second is called heat current, as potential difference, electric potential difference constitute electric current. Similarly, the temperature difference constitute heat current, that is heat flowing per second. Okay, and again for getting the expression for thermal conductivity, you have to think kinetic theory of perfect gas. And again I am telling you, when you will watch my playlist on thermal conductivity in the playlist of thermodynamics of my channel. You will get videos on transport phenomena, okay, and on thermal conductivity. And there you will find that what is the thermal conductivity obtained by using the kinetic theory of gases. Okay, so here I will write directly the expression for thermal conductivity of electron gas on the basis of kinetic theory of gases. Okay, so you have to remember it and you have to write down directly here, because this is just studied in the case of kinetic theory of perfect gas. Okay, so I have mentioned, you can see, as the free electrons behave like molecules of a perfect gas, hence the thermal conductivity K is given like this. You can see this result in kinetic theory of gases. K equal to eta into Cv. Actually here eta, this is coefficient of viscosity, or you can simply say viscosity of this electron gas, and Cv is the specific heat of electron gas. Okay. But when you will watch the video on this viscosity, you will find there that this eta is given by 1/3 mn Vrms into lambda. You can also use V bar, average velocity, instead of this RMS velocity in this expression. Okay. But in examination there is no need to derive this result. If a question will be asked to explain the Wiedemann-Franz law, you have to write in this way. You have to write directly these results, because these results have been obtained in kinetic theory of gases, and the results of kinetic theory of gases can be used in explaining the properties of metals on the basis of Drude theory. Okay, so remember that eta is given like this. This is 1/3 mn Vrms into lambda. Okay, and therefore K will be given by like this. K equal to, instead of eta we will now write this, and so K will be equal to 1/3 times mn Vrms lambda into Cv. Each term in this expression you know. Okay, but you know from the definition of a specific heat capacity. Actually, a specific heat capacity is defined as, this is heat energy needed to increase the temperature of unit mass by unity. So if you consider that m is the mass of an electron and its temperature is increased by dt, and for this we need energy dE. So for unit mass, in increasing the temperature by unity, the needed heat will be 1/m dE by dt. And according to the definition of a specific heat, this is the value of a specific heat. So Cv is defined like this. This is 1/m dE by dt. So in the expression of this K defined in this equation 3, you can replace this Cv by this expression. Okay. So we can write, first of all, we will also see that this E, what is this E? This is actually energy, average translational kinetic energy per electron, one electron. Okay, and according to kinetic theory of gases, this E will be given by 3/2 kb into T, and therefore dE by dt will be equal to what? This will be 3/2 kb, because dt by dt will be 1. So now we will find the value of Cv. This will be 1/m into dE by dt. But dE by dt, this is 3/2 kb. So Cv is simply equal to 1/m times 3/2 kb. Or you can say this is 3 kb divided by 2m. Now let us substitute this value of Cv in the expression for this thermal conductivity K of the metal defined in this equation 3. So replace this Cv by this value 3 kb by 2m, and then you will get K is equal to 1 over 3 m n Vrms lambda times 3 kb divided by 2m. Now you can see this 3 and this 3 will cancel out, this m and this m will also cancel out, and that's why you can say K is equal to 1 over 2 n into Vrms into lambda into kb. Okay, so this is our final expression for the thermal conductivity of metals, which have been obtained on the basis of Drude theory applying the kinetic theory of gases. Okay, now we have obtained in this equation A2 the expression for the thermal conductivity of metals, and in this equation A1 you have obtained the expression for the electrical conductivity sigma of the metal. Now let us divide this K by sigma and substitute the values of K and sigma which we have obtained just now. Now you can see K is equal to n Vrms lambda kb divided by 2 and divided by sigma, but sigma was Ne square lambda Vrms divided by 3 kb t. So as it is in denominator, so this will be in multiplication, this will be 3 kb t by Ne square lambda times Vrms. Okay, now cancel out the common factors in numerator and denominator. N will cancel out, Vrms will also cancel out, lambda will cancel out. Okay, lambda will also cancel out, and now bring this t in LHS, and so you can see this will be K over sigma t equal to 3 over 2 times kb divided by E whole square. Now you can see kb, which is Boltzmann constant, and you know Boltzmann constant is a universal constant having this value 1.38 into 10 to the power minus 23 joule per Kelvin, and E is the electronic charge, and its value is 1.6 into 10 to the power minus 19 coulomb. Since kb and E both are universal constants, so RHS of this equation A is a universal constant, and therefore you can say that this kb by sigma into T is a universal constant. Can you remember what is this? I have mentioned earlier in this lecture that this K over sigma T is equal to universal constant. This is nothing, this is simply the Wiedemann-Franz law. So you can see how easily we can obtain this Wiedemann-Franz law, or we can explain the Wiedemann-Franz law on the basis of Drude model. Okay, so this is the explanation of Wiedemann-Franz law, or the deduction or derivation of this law on the basis of Drude theory. Okay, I think you have clearly understand each and every step of this calculation and this discussion. Okay, now actually this law which is called Wiedemann-Franz law, this law actually holds good for a large number of metals for a large temperature range. This law holds for a very large number of metals when the temperature lies between plus 100 degrees C to minus 100 degrees C. Okay, but at a very low temperature, this ratio K by sigma decreases, and when the temperature T tends to 0 Kelvin, then K over sigma tends to 0. It means in the very low temperature region, this law does not hold good, because when T tends to 0 Kelvin, then K by sigma tends to 0. It does not remain constant like this. Okay, and it is also clear from this relation that K by sigma is equal to 3 by 2 kb E ka whole square times T, and when T will be 0, then this K by sigma will be 0. Okay, so it is found that this ratio K by sigma tends to 0 when T tends to 0 Kelvin. But why this takes place? In fact, it is found that when the temperature of the metal is decreased, both K and sigma decreases. I have also mentioned this fact in the beginning of my lecture. So with decreasing K and sigma, with decreasing temperature, not K and sigma, when you decrease the temperature of the metal, then both K and sigma will increase, not decrease. I have mentioned wrongly initially. But the increase in sigma is much more than the increase in K. At very low temperature, this ratio does not remain constant. Mark it. And when you are talking about a temperature in the region of 0 Kelvin, then actually this sigma becomes infinitely large. But K remains at a finite value. So you can see when T tends to 0 K, then sigma tends to infinity. But K remains finite. Okay, so it is clear that if sigma becomes infinity but K is finite, then what will be this K by sigma? Finite divided by infinite will be 0. So K by sigma tends to 0. So you can say that this Wiedemann-Franz law is not valid in case of the very low temperature, but it holds good between the temperature lying between minus 100 degrees C to plus 100 degrees C. Okay, but in the temperature region of 0 Kelvin, this law fails, because in that condition K and sigma do not increase in same ratio, but the increment in sigma is much more greater than the increment in K. Okay, and so in this condition you can say when T tends to 0 K, sigma tends to infinity, it means our metal now behaves like a resistance-less path. And this state of the metal is called superconductor. So this fact corresponds to the superconductivity state of the metal. So as you will decrease the temperature of a metal, the conductivity of the metal will increase, and when the temperature approaches the 0 Kelvin temperature, then the metals behaves like a superconductor. Its conductivity becomes almost infinite, very large. Okay, so I hope you have understand this very important application of Drude theory, which explains the Wiedemann-Franz law. And I hope there is no doubt in your mind. So watch the video seriously, write down these things in your notebook, and that will be a very good notes for your examination purpose. Okay, thank you very much.